Okay, so we are going to talk about sequences, recurrence, binary, and hex. A sequence is just a function whose domain is subset of the integers. Instead of using the f of n notation, we use a sub n equals f of n, right? So we use an n as a subscript instead of an n inside the f. So the subscript denotes the domain variable, an is the range variable, and this introduces some notation that you'll see in the future. So let an be 4n minus 3 with n greater than or equal to 0. So set up a partial table. What's a partial table? Well, it's just the usual table you'd set up for x and f of x, except now we've got n and a of n. So if n is 0, 1, 2, 3, what do we get when we plug those numbers in for n? Well, if n is 0, we get minus 3. If n is 1, we get 1. If n is 2, you get 8 minus 3, which is 5. And if n is 3, you get 12 minus 3, which is 9. So A0, A1, A2, A3, just plug them in. What's A104 equal to? So that's going to be 4 times 103 minus 3. And if you grind that out, that turns out to be 413. And I'm using my tablet here, so my handwriting is going to be a little shaky. What is this thing here? That means summation. So that's a Greek letter sigma, capital sigma. I equals 3 to 7. What's that? A sub I. Sigma stands for sum. It means we're adding together these things. So we're going to start with A3 plus A4 plus A5 plus A6 plus A7. So 3 to 7, that means we just want to take the terms from n equals 3 to n equals 7 and add them up. What are these terms? Well, we know A3 is 9. You can calculate the rest. A4 is 13, A5 is 17, A6 is 21, and A7 is 25. So we're just adding up those terms, and if you crank out your calculator and add that up, that should be 85. So this symbol here is a sigma, capital sigma. It stands for sum. A capital P, like this, that stands for pi. That's a capital pi, and that means that I want a product. So pi from I equals 2 to I equals 4, and that's an I, should have a little dot over it. What's that? Oh, A sub I. What does that mean? That means A sub 2 times A sub 3 times A sub 4. And what are those numbers? A sub 2 is 5 times, is it times 9 times 13, and that is 585. So just some symbolism there. A sigma is a sum, a pi is a product. Re-indexing the sequence of the domain is n greater than or equal to minus 5. So right now we're starting with n equal to 0. You plug in 0, you get that. What we want to be able to do is to say instead, what's a formula if we're starting with n, an, and we want to start with minus 5, minus 4, minus 3, dot, dot, dot. And we want the same numbers here to come out. Minus 3, 1, 5, and the next number is 9, etc. So how do we move those over? Well, if we think about this just as a function, what's the graph of this function look like? At n equals 0, y is minus 3. At n equals 1, y is 1. At n equals 2, y is 5, etc. Right? So those are points in our sequence 0, 1, 2, minus 3, 1, 5. And what we want to do is move this 5 units to the left. So how do we move a graph 5 units to the left? Well, replace n by n plus 5. Remember, if you were trying to move graphs around back in algebra, to move something to the left, you move it by x, you change the variable from x to x plus 5. So if we take an equal to 4 times n plus 5 minus 3, and what's that? It's 4n, and 4 times 5 is 20, minus 3 is plus 17. And we notice if we take minus 5, you get minus 20 plus 17, that's minus 3. If you take minus 4, you get minus 16 plus 17, that's 1. If you take minus 3, you get minus 12 plus 17, that's 5. So this formula gives you the correct outputs, but starting at n equals minus 5 instead of n equals 0. And what's the relationship between an plus 1 and an? Well, what is an plus 1 anyway? That's what I get when I plug in n plus 1 for n. Oops, don't want that. It's 4 times n plus 1 minus 3, which is 4n plus 4 minus 3. But these two terms, the 4n minus 3, that's exactly what an is. So, still getting used to this tablet a little bit. An plus 1 equals 4n minus 3, which is an, plus 4, right? That is by 4. This is called a recurrence relation, because what it does is it gives us recurrence. That's supposed to be an R. That's supposed to be an E. Relation. Should close my A's. Because it tells us what the next term is, the n plus 1 term is, in terms of the previous term, an. And you can see what's going on here, right? Each an, you're just adding 4 each time to the previous number. So what is recursion? Recursion is a feedback loop. It looks like this, more or less. You take your input, you have some process. Do you exit? Well, if the condition says exit, you exit. If not, you go back and you repeat the same process. This is an important part about recursion. You repeat the same process. You just keep going until you get to your exit condition, and then you leave. So the mathematical notation for recursion draws on this notation for a sequence. If you're given an initial condition A0, the process will give you A1. If you don't exit, you'll get A2 from that. If you don't exit, you get A3 from that. If you don't exit, you get A4 from that. If you need to exit, you output A4. So suppose a classic example of recurrence is suppose you deposit a certain amount of money in a bank, call it P, that's your principal. The annual interest rate is I, expressed as a decimal. Each time interest is compounded, the amount A times I is added to the account, where A is the amount in the account. How much is in the account after n compounding periods? So what do we have? Oops. We have, okay, there we go. A0 equals your principal P. That's our input. And it goes into the process. And what's the process? You take your input, that's A0, and you calculate the interest, which is A0 times I, and that gives you a new amount, which is A1. Right? So that's the process that we're doing. We've now got to the exit. Is that we've done it once? Is that as many times as we want? Well, no. Let's go back to the process. But now we're going to be using the process using A1 as the input. So if A1 is the input, what do? We take the number we're given, A1, and we add to it that, I, and that gives me A2. And you can keep going as long as you want until you get as far as you want. Every time you take the previous output, add A1 times I to it. We can simplify this a little bit. if you factor out the A0, you get A0 times 1 plus I equals A1. If you factor out the A1 here, and so we can see what we're actually doing here is we're taking the number 1 plus I and we multiply it by our input to get an output. Take that output, multiply it 1 plus I, we get A2. Take that output, multiply by 1 plus I, we get A3. So we get a sequence. A0 is how much you've had after, that's how much you put in. A1 is how much you had after 1 year. A2 is how much you have after 2 years. A3 is how much you have after 4 years, etc. What's the formal recurrence relation? Well, each number, an plus 1, is 1 plus I times the previous amount. So how much do you have in the n plus first year? Well, you take 1 plus I, you multiply how much you had at the nth year, and that'll give you the next year. What's the closed form expression? So this is the recurrence relation. It tells me that if I have an, I can get an plus 1. What's the closed form expression? That's something like this. That's a nice little expression that has an equals something. It's a function of n. It doesn't have any other an's in it. So what we can look at is A1 is 1 plus I times A0. A2 is the same thing. It's 1 plus I times A1. But now we know that A1 is 1 plus I times A0. So this becomes 1 plus I times 1 plus I, dot my i's, times A0. Because this part here, that's all A1. So A2 is 1 plus I quantity squared times A0. A3 is just 1 plus I times A2. So A3 would be 1 plus I cubed times A0. So in general, you can get a closed form expression, AN equals 1 plus I to the n times the amount that you put in. So this is a closed form because the right-hand side here doesn't have any ANs in it. It just gives you the n. If you want to know how much you have after 100 years, you can just plug it in. If you want to know how much money you have after 100 years using this, you have to run through all 100 cases. Okay. So continuing on, we'll give you a definition of a recurrence relation. It's this with initial conditions. So here's a recurrence relation. An equals an minus 1 plus an minus 2. These are the initial conditions. The order of this thing is 2. Because we go down to n minus 2. So just telling me that each term can be defined in the previous terms. The initial conditions are these two. They tell you what A0 is and A1 is. What's the first 6 terms? Well, we know A0 equals 1 because they tell us that. We know A1 equals 1 because they tell us that. They don't tell us what A2 is, but we know that A2 is A1 plus A0. And that's 2. A3, well, 3 minus 1 is 2, so that's a sub 2 plus 3 minus 2 is 1 plus a sub 1. So that's 2 plus 1, that's 3. A4 is A3 plus A2, which is 5. Right? What's A5? A5 is A4 plus A3, which is 3 plus 5 is 8. Okay, so that's 6, the first 6 terms. Why do we only go to 5? Well, we started at 0, right? So 0, 1, 2, 3, 4, 5, that's 6 terms because we started counting at 0. This is something called the Fibonacci sequence. You may have seen it before. What's A100? Well, to get A100, you have to grind through this a billion times. Luckily for me, I have Microsoft Excel, and it can tell me what this is. I don't know how to say this number because it's too big. But I just wanted to write it out just for fun. 817 0 0 0 0 0 0. So that's the 100th term. If you did this 100 times, you get that number. It's quite large. So where do recurrence relations show up? They show up in a lot of different contexts. Here's kind of a nice context, a kind of a jocular one. Suppose you can go upstairs either one at a time or two at a time. And the two at a time is just by hopping or jumping or whatever. So what's a recurrence relation? Describing if you have a flight of n stairs, how many ways there to go up there? So if you have a flight with no stairs, there's one way, just take one step. If you have n equals 1, and that's what this is supposed to be, this is supposed to be an n, right? So we have one step, there's one way to do that, because you just take a step. So n steps, dot, dot. How many ways are there to go up a flight of stairs with n steps? That's supposed to be an E. Well, two ways to do it. You can either take one step, go up one stair, and then you have a flight of n minus 1 steps to do. Or you could do a hop, and then you have a flight of n minus 2 steps to do. So we'll let an be the number of ways to go up a flight of n stairs. What we saw was that a0 equals 1, a1 equals 1. In general, how many ways are there to go up a flight of n stairs? Well, either you take one step, right, one step, and then you have to go up n minus 1 steps. But that's what an minus 1 stands for, right? That's the number of ways to go up a flight of n minus 1 steps. Or you could take a hop and go to the second step, but then you have n minus 2 steps left to go up, and that's what an minus 2 is. An minus 2 is the number of ways to go up a set of n minus 2 steps. So in fact, this is the Fibonacci sequence again. And the Fibonacci sequence shows up in a lot of different contexts. You know, if you have an option of doing either one thing or two things at a time, you end up with a Fibonacci sequence. So this is an example of how to construct a Fibonacci sequence. What is A100? If you had a flight of 100 stairs, how many ways are to go up that? Well, that many. Lots of different possibilities. So finding the occurrence relation, you have to go through all of these things. We want to be able to solve recurrence relations, and a solution or closed form for recurrence relation is some function an equals just something with n's on it, not something with these an minus 1 plus an minus 2s. So how do we know if something is a actual solution? How do you find this? You plug it in, right? How do you tell if something's a solution? Plug it in and see if it works. So an, our possible solution, is 1/2 n squared plus 1/2 stop that, 1/2 n. So that's what if I take an and I multiply it out, I get this. That's my left-hand side. So we'll write equals left-hand side. The right-hand side, that's this part, is n plus an minus 1. So that's n plus, and now an minus 1 is what we get when we plug in n minus 1 into this formula. 1/2 n minus 1 That's when I plug in n minus 1 for an n. If I plug in n minus 1 for an n in this term, I get n minus 1 plus 1, which is just n. So my right-hand side equals n, that's this term, plus whatever this is multiplied out, which is 1/2 n squared minus 1/2 times n. And what is that? N minus 1/2 n is 1/2 n plus 1/2 n squared. So my left-hand side and my right-hand side are actually equal. They're both 1/2 plus 1/2 n squared. So this is a solution. So the point here is, if you want to check that something is a solution, a closed form is a solution, plug it in. Just remember, when you plug in a n minus 1, you have to replace all your n's by n minus 1s to get your right-hand side. Okay, so a particular type, a very common type of recurrence relation can be solved. It's got a solution scheme. So linear, homogeneous, constant coefficient recurrence relation of order k. It's this. And these are just constants, C1 times a n minus 1 plus C2 times a n minus 2 plus dot, dot, dot. So which one of these are of this type? So this is, that's degree 2 or order 2. I've got an equals this term plus 3 times that term, so I'm allowed to multiply by constant. That's okay. Second one is not. Right? The plus n is the problem. I'm not allowed to have the variable all by itself. The third one is not of this form. Can't multiply terms together, right? I have an minus 1 times an minus 3, and I have to have them separated by plus signs. And this one is, and it's of order 4, because we go down to n minus 4, so that tells me what the order is. So 4an minus 2 minus 3an minus 4, that's perfectly good because I've got constant times an an term minus a constant times an an term, not allowed to multiply n terms, not allowed to have n all by itself. Okay, so here's an example that'll show us how to solve these sorts of things, and then I'll state what the procedure is and do a couple of examples. So how do I want to solve this? Note from example 2, what we got was an equals 1 plus I quantity to the n, and that's an I, times a0. The important point about this is a number raised to a power, and then something involving the initial condition. So what I'm going to assume in order to solve this, and this is not, if you're actually going to be solving these equations, don't do it like this, follow this procedure. This is sort of explaining how it comes to be. I'm going to set an to be t raised to a power, some number, which I don't know, I have to quit pressing on that stupid button, t raised to some power, n. So an should be a number raised to the n. How do I find that? Well, if I substitute in, how do I substitute that in? Well, an minus 1 would be t to the n minus 1. An minus 2 would be t to the n minus 2. So if I plug all that into my equation, what do I get? I get t to the n equals 5 t to the n minus 1 minus 6 t to the n minus 2. Then we can simplify that by dividing by t to the n minus 2 all the way through. If I do that division, t to the n over t to the n minus 2 is t squared. T to the n minus 1 over t to the n minus 2 is t. And then the t to the n minus 2's cancel out. So if t squared equals 5t minus 6, I look at that and I think, I know how to solve that for t, because that, if I move everything to the left side, is a quadratic equation. And I know how to factor that. So I've got two possible solutions, t1 equals 3, t2 equals 2. So I want to know, well, if I've got these things and my an should be these t's raised to a power, what could an be? I need to take into account both of them. So I'll write an equals some constant, which I don't know, times 3 to the n, that's this term, plus some constant I don't know, times 2 to the n, that's this term. This thing here is called the general solution. And it's called that because we have not yet used any information about the initial conditions. So what are B1 and B2, question mark? Well, if we have A0, we know on the one hand that's 1. On the other hand, if I plug in 1 into the 0, if I plug in n equals 0 into the general solution, I get B1 times 3 to the 0, and 3 to the 0 is just 1, plus B2 times 2 to the 0. And I know A1, that's my other initial condition, is equal to 4. On the other hand, if I plug 1 into the general solution, I get 3B1 plus 2B2. And I need to solve these two equations for B1 and B2. So how can I go about doing that? I'll take the top one and multiply it by 2. That gives me 2 equals 2B1 plus 2B2. And the bottom equation is 4 equals 3B1 plus 2B2. I'll subtract the top equation from the bottom. 4 minus 2 is 2. 3 minus 2 is just 1B1. 2B2 is 0. So now it tells me what B1 is. B1 equals 2. If I plug that back into this equation up here, if this is 2, B2 has to equal minus 1. So that tells me the specific solution. Specific solution. A sub n equals B1, which is 2 times 3 to the n, plus B2, which is minus 1 times 2 to the n. And I write out what's A100. Well, I can actually calculate that now. I just plug in n equals 100 into this equation, and I can figure that out. It's something that's got, how many decimal points does it have? 49 digits. It's a very long number. But that's the procedure. That's where it comes from. It comes from the idea that if we try to solve these kinds of problems, right, you're going to get something raised to a power, t raised to the n. You can find the t's by looking at this quadratic, t equals 3 and t equals 2, and then that gives you a general solution. If you have initial conditions, you can evaluate them to figure out what the specific solution is. So here's the procedure. If you've got this kind of a thing, set up a quadratic equation, t squared equals c1t plus c0. So this becomes a t squared. The n minus 1 becomes a t. The n minus 2 becomes a 1. Solve the equation. It's a quadratic equation. Generally, you get two different solutions. Sometimes you get one. If you have two different solutions, like what happened here, the general solution is b1 t1 to the n plus b2 t2 to the n. Plug in n equals 0 and equals 1 using the initial conditions and solve the equations you get to get b1 and b2. If you have just one solution, which is sort of a special case, the general solution is an equals b1 t to the n plus b2, and then there's an n times t to the n. And then you do the same thing to get b1 and b2. So as a couple quick examples, here, solve this equation. Well, we set up the equation t squared equals 4t plus 21. Change the an to a t squared. Change the an minus 1 to a t. This is a quadratic. If we move everything to the right side, remember how to factor. This becomes what? T minus 7 times t plus 3. So I have two roots. T1 equals 7. T1 equals minus 3. So what's my general solution? B1, 7 to the n, plus B2, minus 3 to the n. The minus sign can't come out of the parentheses because sometimes n is even, sometimes n is odd. So if n is odd, you'd get a minus sign. If n is even, you wouldn't. So that's my general solution. Now that I have general solution, how do I find B1 and B2 to make it a specific solution? Well, A0 is 1. So 1 equals B1 plus B2. How did I get that? Well, if I plug in n equals 0, A0 is 1. B1, 7 to the 0. 7 to the 0 is just 1, so I get B1, and then B2 minus 3 to the 0. That's going to be 0. A1 is 27, so if I plug in n equals 1, I get A1 is 27. Then I get 7 times B, because 7 to the 1 is 1, and then minus 3B2. So if I plug in n equals 1, I get A1, which is 27, is B1, 7 to the 1, so 7B1, plus minus 3 to the 1, which is minus 3 times B2. So there's my two equations. So how do I solve that? I'll multiply the top by 3. Leave the bottom one alone. Why do I do that? This is 7B1 minus 3B2. Now when I add them together, the B2s go away. So when I add these, I get 30 equals 10B1. B1 equals 3. And if B1 equals 3, if this is equal to 3, then B2 has to be minus 2. So my specific solution is 3 times 7 to the n minus 2 times the quantity minus 3 to the n. Okay, what about this relation? Okay, so we start off in the same way. We turn it into a quadratic. T squared equals 6t minus 9. We move everything over so we can solve this. We say, I know this. This is a perfect square. So now we're in case 2 because we only got, right, well, in this case, because we only got one root. So what's our general solution? And a sub n equals B1, 3 to the n, plus B2 times n times 3 to the n. So that's our general solution. What's our specific solution? Well, plug in the initial conditions again. 1 equals, if n equals 0, we get B1. And then if n equals 0, this whole term goes away because it comes B2 times 0 times 3 to the 0. And then the second equation is 9, right? If n equals 1, oh, that should be an A1, not A2. 9 equals 3B1 plus B2. N is 1, so 3B2 times 1, and so it's just that. And that's a 2. So my two equations are 1 equals B1, and if I divide everything here by 3, 3 equals B1 plus B2. And so since B1 is equal to 1, that means B2 equals 2. And so my solution, AN equals, B1 is 1, so 3 to the n, plus B2, 2n, 3 to the n. That's my solution. It's not super complicated, but you do need to practice it a little bit. These sorts of things come up a lot when you're trying to figure out runtime of any kind of a loop, right? Because when you're doing a loop, You're going to run through it over and over again until you get to the end. And the question is, well, how many times you're going to run through the loop and how many calculations you're going to do. That's a recurrence relation because you're feeding the same process. Take the output, feed it back into the same process. So you'll see these when you're trying to figure out how long does my program take to run. So last thing is just thinking about different bases. Base 10, base 2, base 16, but any number can be taken as a base. So binary is base 2. So here's a binary number, 1011, and we want to convert it to decimal. What does that mean? Well, this is my 2 to the 0 coefficient. That's my 2 to the 1 coefficient. That's my 2 squared. That's my 2 cubed. So if I want to write this out, it's 1 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the first plus 1 times 2 to the 0, right? When you're thinking about how numbers work, if we had like, 200, 217, 7 ones, 110, and 2 hundreds. So 1011 means 1 1, 1 2, 0 4s, and 1 8. So it's 8 plus 2 plus 1, which is 11. Okay, so binary to decimal, not too bad. How about decimal to binary? So we have 139. So 139 is going to be equal to some sum of powers of 2. And 139 is between, these are the powers of 2. 139 is between 128 and 256. So I can write this as 128 plus 11. And 128 is 2 to the 7th plus, and now we know what 11 is, 8 plus 2 plus 1. So this is 2 to the 7th plus 2 cubed plus 2 to the 1st plus 2 to the 0. So what do I need? I need a 1 for my 2 to the 0, a 1 for the 2 to the 1st. I don't have a 2 squared, so I put a 0 there, but I do have a 2 cubed, so I put a 1 there. Don't have a 2 to the 4th, don't have a 2 to the 5th, don't have a 2 to the 6th, but I do have a 2 to the 7th. So 1 1 1 0 0 0 1 0 1 1. The 2 to the 0, the 1's part, that's at the right. Then you just go up. How many digits is that? That's 8 digits actually, right? Because our number is between 2 to the 7th and 2 to the 8th. But we start counting at 0. So I need a 2 to the 7th place, but that's 1, 2, 3, 4, 5, 6, 7, 8 digits that I'm going to need. Okay, so what's a slightly faster way to do that? You can do it by cutting things in half, which is quite nicely. So 405 is, if you cut it in half, it's 202 with a remainder of 1. If you cut 202 in half, you get 101. I should actually not have equal sign, but little arrows. Is 101 with a remainder of 0. If you cut 101 in half, you get 50 with a remainder of 1, right? 50 times 2 is 100 plus 1, that's the remainder. 25 with a remainder of 0, 0. Half of 25 is 12 with a remainder of 1. Whenever it's odd, you pick up a remainder. 6 with a remainder of 0. 3 with a remainder of 0. 2, nope, 1. Half of 3 is 1 with a remainder of 1. Then half of 1 is 0 with a remainder of 1. So what's my number? 1 1 0 0 1 0 1 0 1. Start at the bottom and work your way up. So 405 is between 2 to the 8th and 2 to the 9th. So we should have 9 digits. 1 2 3 4 5 6 7 8 9 digits. And why is that? It's because 2 to the 9th is 512, and 405 is between 256 and 512. So in general, if we want to convert a number to binary and we want to know how many bits that take, every bit is either a 0 or 1. How many bits of memory do I have to have if I want to store this number in binary? Well, what we've seen before is if we can find an n that's smaller than the number, I'm not going to write this number out. It's just whatever that number is. And less than another power. Then this power, the 2 to the n plus 1, that's how many digits you've got, right? So 405 is between 256 and 512, so it needs 9 digits. 139 is between 128 and 256, so it needed 8 digits. So how do we get exponents out of the exponent? Take the log. So log base 2 of 2 to the n should be less than or equal to log base 2 of whatever that number is up there. That should be less than or equal to log base 2 of 2 to the n plus 1. Oops. Did it again. So log base 2, 2 to the n, that's just, if we take this equation and move it up here, n less than or equal to this. Log base 2 of whatever that number is, you can go and look that up on Excel or someplace, or from Alpha. It's 28.95. And that should be less than 9 plus 1. So what's the integer that's bigger than 28.95? That's 29. So we need 29 digits to figure that out. Okay, so that's base 2. Base 16 is a similar thing, except we only have 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we need to have extra digits. A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. Remember that 1, 0 is 1 times 16 plus 0 times 16 to the 1 plus 0 times 16 to the 0 equals 16. So 1, 0 actually means 16. It doesn't mean 10, so that's why we need these extra symbols. So convert 405 to hexadecimal. How do we do that? Well, 405 is between 256 and 4096. So 405 will be 256 plus something. 256 times something. So it's going to be 256 plus, what's after that? 49. So 1 times 256, and if we subtract that off, we get 149. So we want to write 149 as something times 16, and 256 plus, now 149 is 9 times 16 plus 5 times 1. Stop that. Great, so what have we got? 405 in decimal is 1 16 squared plus 9 16s plus 5 16 to the zeros. So it's 195. What's A2F in decimal? Well, that's going to be F is, let's see, 10, 11, 12, 13, 14, 15. 15 times 16 to the 0. 2, well, that's easy. 2 times 16 to the first. And then plus A is 10. 10 times 16. So this is the 16 to the first column. This is the 16 column. This is 16 squared column. If you multiply all that out, you get 2607. How long is this string if you wrote it out in decimal? It's the same one we had up there. Well, you take the log base 16 of that number, and you get 7.23. So in hexadecimal, it would be 8 digits. Right? And this is 1, 2, 3, 4, 5, 6, 7, 8, 9 digits in decimal. 16 is bigger than 10, so you need fewer digits to write it out in hex. 2 is less than 10, so you need more digits to write it out in binary. And in fact, if you go look this up, I think this is 1E, F, B, E, D, 2A. Although this might be a 0 because my handwriting sucks. Okay. How do you add things in hexadecimal? 13E plus F5. It's the same procedure as writing in decimal. 5 plus E is what? Well, you go up to the table, here's E, and you want to go 5 more. So 1, 2, 3, 4, 5. You get a 3, but you went from F back to 0, so you have to carry a 1. F plus 3, start at F, add 1, 1, 2, 3, and then the 1 that you carried, that gives you a 3. But adding F, you have to go back into the cycle, so you have to carry a 1 again, and then we get a 2. So that's 2, 3, 3. So pretty straightforward, adding in hexadecimal, adding in binary. So recurrence relations show up a lot. There's a way to solve them if they're of a particular form. And then some stuff about these bases.